for joining this on 3D basin modeling, unlocking hydrocarbon potential through advanced geological simulation. My name is Dr. Mahmoud Yusuf, and today we will explore how basin modeling has evolved in one of the most powerful tool for reducing exploration uncertainty and improving petroleum system understanding. Throughout our session today, inshallah, we will discuss the fundamental of basin modeling, its application in hydrocarbon exploration, different modeling approach, the difference between 1D, 2D, and 3D modeling, source rock evaluation, migration analysis, practical case studies from major petroleum provinces. Let's start sharing my screen. Okay, first of all, we're here for answering any question you need. If anyone don't want to ask a question for on public, please drop your question on the chat, and the final of our webinar, we will answer all the questions. Let's share my screen. Now it's clear.
Yes, it is. We can see your screen.
Okay, very good. Okay, let's begin with the fundamental question. What exactly the basin modeling? Basin modeling is a numerical simulation of geological process occurring with the sedimentary basin through geological time. This is important. The key aspect of the basin modeling, we have three key aspects for the basin modeling: the purpose, which is the objective, to reduce mainly the exploration risk by the modeling the petroleum system, source rock and maturity, timing and generation, and migration pathways. Component model, it simulates sedimentary basin evolution, including compaction, pore pressure, development, and heat flow history through time, effect of the structure like rifting and heat thermal flow, and so on, which are affecting the thermal maturity or the maturity of your fields. The workflow that we need for the 1D, 2D, and 3D basin modeling, first of all, we need a structure model geometry, which is the framework for our work, followed by reconstruction of the burial and thermal history calibrated with actual data like vitrinite reflectance or the well temperature. The role of the basin modeling is to reducing our risk. This is the main object of our model. Basin modeling, petroleum industry as well faces a lot of uncertainties in petroleum exploration. Our role is to decrease this uncertainty. Basin modeling helps to reduce this uncertainty by answering critical exploration questions like, was there a work source rock in your field? Did it generate hydrocarbon or not? Did it generation occur after or before the trap? And this is a very, very important note, which we called it about critical moment. If the migration is occur before or after your trap, each one of them has a different meaning, and which is one is a critical for your exploration and development of your fields. Could hydrocarbon migrate into the trap or not? This is very important, especially in the exploration phase. If you take a one new province that we work on it for the first time, did the seal retain the accumulation? You have a good trap, you have a good seal. Did your seal have a capability to accumulate your hydrocarbon and retain it inside the trap or not? This is very, very important. All of this rule for the exploration is used for the exploration risk. This is mandatory by answering this question before drilling or working in exploration phase, as we can reduce the dry hole risk and prioritize the most promising prospect. For the 3D basin modeling, we just will not jump, just quick exploration about it. We can give it for the software, the prospect, the polygon, and so on. And after that, you can discuss the migration pathways, and it's reached your prospect or not. If the model says the prospect is filled or migration reached to this prospect, we have 50% or 60% priorities to just drill this one first. If there is no migration pathways from your model reach to your prospect polygon in the exploration phase, we can use it as the last prospect we can drill, or we can neglect it as all. So the Bayesian modeling itself from the 2D to 3D is very important and essential for your economic decision, especially in exploration phase. So the main petroleum system that we need, the function petroleum, it required several essential components to work. We need a lot of components should contain together and compatible together to get your model right. First of all, the source rock. The source rock is the most important one, including the TOC and the organic matter sufficient to produce hydrocarbon. Reservoir rock, which have good porosity, good permeability, which we can call it carrier rock, which can hold the hydrocarbon. Sea rock, which can retain your hydrocarbon inside your trap. Migration pathways, and this is the most important one. This one maybe is not considered on the petroleum system elements, but it is very, very important, especially in the 3D Bayesian modeling, if it's reached your prospect or not. It is very, very important. We consider it, we can use it by using Petro mode or Petrel software. It is mandatory to see your migration path from your kitchen, from the time of generation, and the first expulsion, and the time of your traps. If any one of this element is absent or ineffective, the hydrocarbon accumulation may not be formed. So we start first with the source rock, the first element that we search for it. If it's present, we will search for the reservoir rock. After that, the sea rock, the third one, migration path, reach to your trap or not. And finally, the presence of the trap. Maybe you have a good reservoir, but you didn't have a trap stratigraphy or structure that can holding your hydrocarbon. So Bayesian modeling evaluate not only the presence of this element, but also their timing and the interaction. It is very, very important. The time is the most important rule, and it is the most tricky element on the 2D and 3D Bayesian modeling. The timing is very, very important. If you don't have a good timing interaction, maybe you have all this element together, but actually the timing of the critical moment or the timing of the first expulsion will be before, after your trap or before your trap. At this case, you found nothing. You will lose most of your hydrocarbon on another trap or outside to the surface, like we face in Gulf of Suez, as example in James Field, like we face in the most probable point or gases escaped from the Mediterranean. All of this is escaped through fault or through a fracture from the carrier rock to the surface. You lose your hydrocarbon. So all of this together with the timing is mandatory for your evaluation. Just a quick recap for the source rock. This contains of should be the rock that we call, say, a good source rock. It should have sufficient organic matter capable to generate hydrocarbon. Most of the source rock present in the world is a shale and carbonate. Sand, of course, sand cannot be a source rock because in this case it have a high porosity, high permeability, is a good carrier rock, but cannot consider as a source. Because there is no organic matter present on the sand because it's deposited in energetic water. So there is no organic matter can leave on it due to the porosity and permeability present on it. For the reservoir, rockets provide storage space and flow capacity through porosity and permeability. The most famous one for the clastic is of the sandstone, and for the non-clastic is fracture carbonate. Of course, this is for the conventional. For the unconventional, all of this one could be considered as a source and the reservoir as well. For the sea rock, prevent the source that prevent hydrocarbon from escaping. Migration pathways connect source rock to your trap. Finally, trap focus hydrocarbon into accumulation and can be produced commercially. That we can call it trap. Okay, for the Bayesian modeling integration, a lot of data set into one framework. This is, we need a lot of data to build our model. All the data should be connected together with the most good way to build a rest or restable 3D model. It helps to understanding source rock distribution, thermal maturity, hydrocarbon generation, migration pathways, accumulation history, leakage risk, and even oil quality prediction. Of course, after you build your model, you can predict either you can produce oil or gas or two phases together, oil and gas. And also, if you can detect the oil and gas from the 1D model, from the 3D model, you can predict also uh, the API or the expected API for your oil or the quality of your gas. Maybe it will be wet gas. Wet gas, it's not only methane, it's 60% or 50% methane, and more than 50% to 40% from ethane to C15 or C50. For the oil, maybe it is a high API like 41 or 45, which is a good, very good oil API, to the early oil window stage, which the API will not exceed 15 to 16 API. So from knowing your window, actually you can predict your oil quality and your gas quality as well. You can also determine the age of this oil if you have a good sample from the source rock from your fields. You can correlate it with the ACG, the gas chromatograph, or oil fingerprint by the isotopes. You can detect the age of this oil and which coming from any source rock. This is very important to know what is the source of your hydrocarbon, and actually you can also detect your quality of the hydrocarbon. Maybe it's very good for you, especially on the exploration phase, to detect your because in the exploration phase you can work on the facility. You can detect your facility based on the prediction of the hydrocarbon found in your field. If you have a good facility for oil, so you can produce oil. If you predict gas, you prepare the facility of the gas. Each one of them is a high cost. Each one of them need a different configuration. So if you can help them during the exploration phase with this information, you can help the economic or the success of your fields, or just dump your fields and going for another exploration opportunity. For the type of Bayesian modeling, we have three types of the Bayesian modeling: 1D model, 2D, 3D, increasing the complexity. 1D model, it's a very simple one. It's just vertical versus depth. It's building from your well. 2D model, you can detect the cross section of the seismic interpretation. You can end it with your software and just spread your wells and your data of the maturity on it. For the 3D, this is the most common one. You need all your data, seismic interpretation, maps, horizon, faults, and so on. You can build your map. This is the literature saying the 1D, 2D, 3D, 3D increase complexity, but actually I can't confirm on that. If you build a good 1D model, I think the 2D and 3D will be very, very easy. Actually, on the 2D and 3D, it is just combining all this data together and using the software. If you build a good 1D model, which is the mandatory or the important for the calibration, because the calibration stage always depending on the 1D model, because in the 2D and 3D, you just spread your information like the 3D Basin, like the 3D static and dynamic modeling. You just take the data from the petrophysics, from the seismic, from the compaction trend, pore pressure, mapping, so on, and just adding on the software using the betrayal in the modeling as example, and build your model and spread your parameter after the calibration of it. Actually, the 3D based modeling is the same. You build just a framework, building all the data, but actually the difference between them on the 3D static and dynamic model, you can handling if any mistake done by the petrophysicist or by the seismic, you can handle it in your model by interface of the geomodeler can do it. But on the 3 2D and 2D 3D modeling, unfortunately, you will return it back to the first step because all the calibration we done on the 1D model. If your 1D model is wrong, all the data will be wrong. If the 1D model is good, actually it is a matter of using your software on the 2D and 3D and knowing the knowledge. Because just from the TD and 3D, we just expect between the wells. But if you don't have the wells, you have a lot of uncertainty. Of course, as a model, if you have more data, more wells, more 1D model, You can have a robust 3D model if you don't have less, or you have less model, 1D model, or less wells. Of course, you will increase the uncertainty. And by the way, the 3D based modeling is the same like a static model and dynamic model. It is just a process, just done and continue. After any data you added, you will increase the confidence of your model. We will start with a 1D Bayesian modeling. 1D Bayesian modeling is a vertical dimension. It is just vertical depth at a specific location. It's usually using the one well. It reconstructs geological evolution vertically at specific well location. The main output of the 1D model always will be the barrier history, temperature evaluation, pressure evaluation, source rock maturity, hydrocarbon generation time. This is the most critical one on our 3D Bayesian modeling, and this is the main output of the 1D model. Actually, the objective of the 1D Bayesian modeling is reconstructing barrier history, evaluate thermal maturity, determine hydrocarbon generation, acid petroleum system viability, calibration of the Bayesian modeling before we run 2D and 3D modeling. Actually, it is taking from the 2D and 3D the 1D data, calibrated, should be all the calibration steps should be done on the 1D model, just to entering on the 2D and 3D modeling after that. And the model, after using the data, using the depths from the maps, from the faults, from the seismic interpretation, now he can build or predict the maturity by using the relation of the depths and the data actually we found in the 1D model. It's often first step before building a regional Bayesian modeling, and it is the most important step before you run your 3D Bayesian modeling. The key input data for the 1D model, you always need stratigraphic data, lithology, erosion and conformity, compaction parameter. On the stratigraphy, you need formation tops, thickness, geological ages, lithology control, compaction behavior, density evolution. You need it from the sonic log or density log. Erosion and conformity, it is very, very important because it's will affecting the maturity very well. So we just taking in our interpretation, timing, like the uplift, rifting, subsidence, amount of erosion section. It is very important in your calibration. Compaction parameter, because it will affecting the porosity at the shallow depths, decreasing expansion with the burial. Affecting with the compaction will affecting the maturity as well. Here, this is an example for the 1D model. If the data always matched on the 1D model like that, so we have a stable here, there is no structure. Actually, it's very good. There is no structure here. It's just subsidence, normal. After that, here we found some structure. Okay, this is a fault. After that, this is a rift system upward this section. And after that, there is a stable interpretation into the recent new gene. Here, this is PNC. This is represent the temperature and vitrinite reflectance calibration. We should take the data from the temperature log, from the acid. Actually, we have two sources or three sources of the temperature calibration for this point. First one, we take us the geochemical data and just making for this analysis on the lab. Is the best one. The second one for the calibration and is the same like was the first one. It is the temperature from RFT. RFT from the pressure point, not from the normal logs, because the pressure, the temperature recording from the RFT data, actually it is the most corrected one. We use it on the 1D model without correction. Just use it and calibrate with it. But if you didn't record the pressure point and recorded the data, you recorded PHT, the bottom hole temperature. At this one, we need to correct this data by the Horner plot just to calibrate this temperature because it's affected by the mud viscosity, mud circulation coming on the well, temperature during the every log runs, run one, run two, run three, it's always increasing the temperature. So everyone have a different bottom hole temperature reading. The temperature is highly affecting the maturity and also affecting the vitrinite reflectance reading. So you should calibrate the temperature very well and to be more or less very confident and very near from your data coming from your model. Veterinary reflectances are all, it's can be measured from logs, but it's not accurate. It's just a relation of the sonic log and density log. I didn't prefer to use it unless you didn't have any data. If you have a far wells from another fields, you can depend on it. It's the same. If it's the same structure or the same orientation of your field. But if you don't have, يعني don't depend on this tool as it is. Just using from the model and temperature data. Veterinary reflectance coming from the geochemical data analysis. This is the most important one used to use because it predicts the maturity identically. At this case, we calibrated with this point. Should be your point more or less very near from your temperature and veterinary reading or recorded on from your 1D model, just to build a robust 1D model which you used in the 2D and 3D as we mentioned before. The calibration is very important. We can calibrate with the temperature, with the veterinite, and also with the porosity. It is very important tool to ensure this model is good. You should use porosity data because the value of the porosity, total porosity exactly, is very, very important on the building your compaction trend. Because here you can detect the poor pressure, hydrostatic, and overburden. If you have a poor pressure coming from the sonic, it's more and better and better. But if you don't have this point already in the 1D model, he can estimate the hydrostatic pore pressure and overburden. But this is calibrated from your data from the wells. But you need to add more data for it. And from this compaction trend, you can estimate the porosity, the total porosity. If you have the curve already present in your database, you can use it and calibrate your data with it. We can use porosity data, sonic data for the compaction, density log for the rock properties, which is mandatory on determining the maturity, and it will also affecting the window of the oil and the gas and the metamorphism after that. Integration with the thermal modeling, it's very important to use temperature modeling, maturity modeling, hydrocarbon generation. All this step is run only in the 1D model. And after that, if you run and use the proper data, input data is good. And after that, you calibrate it well. So your model on the 2D and 3D will be very easy workflow, very easy workflow. It's not, it's not an issue because all the calibration done in these steps. After that, there is some enhancement between the well. There is the area, there is no data. You can return it to you will depend on the seismic interpretation. If you have a good sign for the interpretation here, maybe the interpretation needs some enhancement, you return it back to your geophysicist and please enhance me this point. And after that, you can entering this one. It will, it's, by depth, by the way, the interpretation is highly affecting the maturity, by the way. If you increase the depths, you will increase the maturity. If you decrease the depths, you will decrease the maturity. And this is the reason why of the compaction affecting your bed or your formation. Actually, more compaction, more maturity, less compaction, less maturity. And this is why the reason we define the oil window, the catagenesis, and the gas window, the metagenesis, with depths and temperature. This is the main factor affecting moving from window to another window. The temperature and the depth. Maybe you have a good source rock, a good TUC, a very high TUC, very high organic matter, very good kerogen, but actually you didn't enter the window of the oil. So at this case, there is no oil present or there is no hydrocarbon present here. Okay, sorry. Okay, the limitation of the 1D Bayesian modeling, there is some limitation on the 1D model. 1D model is dealing just, it is depth versus vertical. This is just inside your well. There is no, you cannot simulate the lateral migration, structure evaluation. Actually, there is only 1D trap formation, regional petroleum system. You cannot see any of this point. You can see any of this point. You cannot see any of this point because it's actually 1D model. You can detect this trap formation and regional petroleum system by using the 2D and 3D model. Here there is a 1D model. This is what I already explained in the previous slide. Here this is accelerated substance is care. Here there is attenuated substance. There is no substance here. This is very good. This is Toposa basin. It is phase. After that we have accelerated substance occur here. There is here a major permeable basin. It's attenuated, after that attenuated substance. This is Cenozoic uplift. We can know this is rifting because this is substance occur. Here there is uplift because the strata here is just uplifting. And this is the uplifted phase for the 1D. You can read from the 1D model the history of the ages from your this 1D model. They represent only one vertical column, as we mentioned, is only on the basin. Maybe if you move from your well, this well, the same basin with a different area on the basin, you will find a different story. Okay, this is an example of the 1D basin modeling. This is a reservoir here present at this level. This is sandstone reservoir. After we run a 1D model, we just found all of this data is in immature stage. It's between 0.25 to 0.55. Did anyone from our attendees expect this layer can be produced or not? And why? Okay. This layer in the reservoir is in this field, and it is a higher layer, and all this section is an immature. The expectation if this layer can be produced or not. From 1D model, what's your opinion? It can produce or not? It's just discussion. There is no right or wrong answer. Actually, no one worked in this field. We just discuss. It can produce or not? Yes,
Uh,
one of our colleagues cannot produce because it's not mature. This is an answer. Does anyone have any other answer? Yes, one of our colleagues wanted to say something. Sorry for disturbance. Ah, okay. No one wanted to add any information? Okay. From the 1D model, if I depend only on 1D model for this layer, of course it will not produce. Actually, because all of this data is in the immature stage, there is no in situ, there is no source rock here. Actually, from the well, it is just migrated the layers, and there is no source rock recorded here. But unfortunately, this layer is producing. This layer is producing and producing very well. It's producing more than 6,000 barrel of oil at this depth with a very high API, by the way. It's reached 239. This layer is produced. If you depend only on the 1D model, you will not rely on any of this reservoir. Actually, you will neglect all this one. But actually, this well is produced from two layers, not only one layer. It's produced from this one and it produced from this sandstone below. Actually, here from the 1D model, you will end up with there is no reservoir here, and also there is no source because all this layer is in an immature stage. But actually, we neglect some point that this is the main issue in the 1D model, the lateral migration. The 1D model can detect the lateral migration of the structure effect. This well is drilling in the horst of the basin, a forest present on the basin. And after that, this basin is just having a main bounding fault. This main bounding fault, the throw is reached to 2000 meter, and the main source rock in the downthrown side of this fault. And it is a very, very good source rock. And the fault with this huge throw, but actually it is the main bounding fault and the main migration path uh, of uh, of this fields. Actually, from this well, oil migrate and just here trap it on this two layer, and this two layer is produced, I think, for more than 10 years with a very stable production. This is the main issue we face on the 1D model because this well is drilling in the forest, so there is no actually, if you see here, if anyone just take a look to the depths, the TD is at 2000 meter. This well is a very shallow well. It's drilling in the forest and actually is produced due to the main bounding fault. But if you take a 1D model for this well, you will end it up, there is no production here, but actually this well is production very well, and this is stable on the production because it is the most higher one in the structure, and all the migration paths reach it to this trap, and we produce from it for very long time with a very stable production rate. This is the main issue we face on the 1D model. The lateral migration, we cannot see it, just a relation between the depth and vertical, actually depth versus time. You cannot see the lateral migration maybe coming from your well from another kitchen. This is not near or that from just vertically below your reservoir. This is a case showing us the integration is very important. And as we say, the 1D model is very, very important, but you should not depend on it is only on 1D model. Finally, the main output that we need from the 1D model is the petroleum system event chart, just to add it the sear rock, the reservoir, the source rock, maturity. Expulsion peak is very important, and also the time. We need, maybe we have different source rock, more than one source rock. As this case, you will have two expulsion rate, two expulsion peak. Also, you have two critical moments for each one of them. Finally, the critical moment should be always after your trap. If the critical moment is below or just before your trap forming, actually this trap will be not filled with any hydrocarbon. This is the main output of our 1D model. It is very important for us to use it. The main output is the time. Actually, all of this may be present, but the timing playing a very important role if this field will be produced or not due to the critical moment and the timing of the formation of each one. Maybe your seal rock is formed after your trap and after the critical moment. At this case, your trap will not be trapped or just have a seal, so it will remove from your trap to another trap or from to the surface. Actually, the time is a very, very important tool in our 3D Basin modeling or the Basin modeling at all. If you lose the time, if you don't know the time, you will lose everything, you will lose all your data. If you know the time, you will build a very robust interpretation, a very robust model. You can depend it on exploration, on the development, and so on. Let's jump for the TD model. Actually, this example for the 2D model is important model to introduce the lateral geological relationship. It is very important because it's neglect the some issues that you face in the 1D model. It enables pressure evaluation, migration path, fluid properties, gas oil ratio, structure influence. Also can qualify production, the gas oil ratio, and their API. This approach the bridge the gap between single well studies and full basin scale analysis. Of course, it's not full business scale analysis because it's fed in the 3D basin modeling, but in the 2D, you can neglect some issues that we face in the 1D model in this 2D model. Let's give a very nice example for the 2D. This is a field. This is the seismic depth converted seismic cross section. This cross section is coming from the seismic, and after that converted to the petro mode. This is the tectonic evaluation, sedimentary evolution of the field. If you found here, this started from A to N. Here, this started with 11.63 million year. Here, this is the faults present in the past. After that, this fault is present in 11 million year. After 10 million years, the area is value high. Now we have two different basins. One basin in the left margin of the basin, the right hand side, and the left hand side, just another basin smaller than this basin because this fault is a major fault. Separate this value high to this major basin. After time from 8.6, 8.1 to 7.5, 7.15, this is still value high. There is no deposition here for all this strata. The deposition is start from here to here. This is a basin high. This is another basin. After the evaluation, it's starting is area to deposit in the value high on 6.3 million year until we reach 2.58. This is still value high. The thickness now is start to be homogeneous. After one at the 0 million year, this is the current time we ended up with the one coming from the interpretation of the geophysicist. Actually, the geophysicist give you this point, just a final step at 0 million year, the interpretation at the current time. On the 2D model, you take this cross section and we can call it in the better mode backstripping. Backstripping, you will return it to the original of the time, older time, and start to build your model step by step, step by step, step by step, by knowing the wells you have, and also the backstripping by your Petromode software or Trinity, by the way. Trinity and Petromode done this analysis. Of course, for the one cross section, you need at least 10 hours to do this step. It's like we found in the dynamic static modeling, the history match as examples take one day, 2 day, just to run the software and still waiting for the result at the end. Actually, you give the software the zero time, 0 million years, and after that you give him the time of every strata for your interpretation, and he started from this current depth, calculating the compaction from the previous history inside the database of the software, and use the depth you give it for the normal compaction trend at the time of 0 million year. He can build your model from 20 million year as example until to the recent 0 million year you reach it the current time. Also, at this level, you can use the kinetic to see the maturity. Here, this is on the right-hand side of the slide. You will find this one. This one is a final cross-section adding the maturity on it, RO. You found here, this is the value high one. There is no maturity. It is immature stage. If you drill here, this is another hint, another first maturity, and here this is the final maturity on the right-hand side. Actually, the most tricky one that we face on the 1D model, for example, that we discussed earlier in the previous slide, if you drill here, you will find all your data is immature. By the way, if you drill a well in the value high, and actually from the previous, the geologist and the exploration always searching for the structure high. Let's drill here. This is the structure high. You have a trap. It's good. Let's drill a well here. If you drill a well here, you should depend on the migration coming from the left and right of this basin. But actually here, from the 1D model, there is no maturity present. If you drill on the left margin of your field, you will find only oil because this green one here is represent the early oil window, and the light green is represent the main oil window, and the very light green is represent the late oil window or the last stage. Here, if you drill another well here, you will find only oil. If you drill a well here on the left margin of your basin, you will find oil and gas and over mature. Here, we reach it to meta genesis, or the metamorphism at the final stage, the blue one. We will find here increasing temperature, increasing the pressure. Here, increasing because here there is no compaction. The lithological column higher than this one is very low. It is very thick. It's very sensory. Here you found thickness of the overburden from the left margin of your field. On the right margin, you have a high compaction, high density of the sediments above this one, increasing the maturity. You will ended up with early oil window, main oil window, late oil window, gas oil window, late oil gas window, and finally the over mature, which here is present mainly dry gas or another site which is called coal. Actually, the position of your well here is always not, you will give not the same result. If you drill here, you will find immature. If you drill here, you will find only oil. If you drill here, you found oil and gas. So the position of your well, all the 1D model you will run for these three wells is right, is correct, but actually you cannot use it alone to build only from the 1D the 3D model. You should use all your data, and this is what we can use it from the lateral migration and the lateral interpretation from your model, just to build it very well, robust modeling, to just build a good 3D model to know your maturation and how you drill and your resource rock. For the 3D Basin modeling, it is the same as 2D, but it is more and more data. Three-dimensional Basin modeling represents the highest level of petroleum system simulation. We use all the data we have. It allows you to just perform kitchen analysis, which one of this kitchen feeding your reservoir, migration pathways mapping. It is a very, very important migration pathways mapping. It's because this arrow lines, it's coming from this map, is mandatory if it's reached your prospect or not. If it's reached your prospect is valid. If it's not reached your prospect, of course, the prospect is not valid. If you have an exploration phase, don't play with this point. If the migration path don't reach it to your polygon or the prospect interpretation, don't drill this prospect. Also, if you are in the development stage, it is very, very important because in the development stage, you have already prospect that's already drilled and confirmed to be a producer. As this case, you can use this arrows to give you oil or gas migration arrows. If the migration arrows you get from your model is oil and you produce oil, so your model is good. If the migration is gas and you produce gas, so your calibration of your model is right. As example, if you have drill another example, another reservoir that produce oil and the migration, you reach it from your 3D model is gas. So of course the calibration of your maturity is wrong. It's totally wrong. You should return it back to estimate or return it back to the geophysicist because maybe the interpretation is not right. Return it to your model and just to correct all this point. If the migration path didn't reach to the prospect that you already produce from it. Of course, the maturation model or the migration pathways map is totally wrong. You should return it back to your model and to build it again because at this level you didn't meet the already produced reservoir on your field. Prospect ranking, this is very important. If you have many prospects and just you want to rank which we start on the drilling to decrease the risk. Quantitative charge evaluation, as we mentioned, if charge is coming to your reservoir or not. Full petroleum system simulation, cover all your area with the R's, with the migration and your corrosion type as well. This capabilities makes 3D modeling invaluable in frontier exploration and the complex geological setting. Just to use it in, of course, in the exploration phase, it's important. But if you have many data or data covering your area, it's very good for you to increase your to decrease your uncertainty. This is an example. This is using Trinity software. It's present on their website. This example illustrates a full 3D petroleum system model. Notice how migration pathways can be visualized through the basin. Also, instead of isolated cross section, this is the difference between the 2D and 3D. The 2D you're just using, just like here, just a section from the 2D, X and Y. But on the 3D, you can add it all the data you have, structure, basin, this is maturation, this is the migration pathways that I already mentioned. This is very, very important. Select your prospect or not. This is the structure of your reservoir. Here, this is the presence of the fault, the presence of the seismic, the maturity level. Also, from using some parameter we use from the 3D, if you have a good geochemical analysis done from many wells, you can use us to detect the the environment, if it's terrestrial or marine or submarine or shallow marine. All of this is affecting the presence of your hydrocarbon and also detecting the maturity level. It's important to add more wells. This is more family, or maybe have more family oil window, or maybe have more family for gases, different gases. It's affecting by maturity for each one because we drill, because after we drill, we get a maturity from for your source rock. And after that, you can see from the ECG analysis, gas chromatograph, and oil analysis, you can detect the component and the family of this oil and the gas. And after that, you can just to connect this data with the data coming from the source rock to know the source of this one, and also to know the environment and to know the quality. The kerogen type, after all of this one, the kerogen type is the most important also factor in the evaluation of your source rock. Source rock is an engine of the petroleum system. Source rock should have effective largely depending on the type of the organic matter known as kerogen. Kerogen determine whether oil or gas will be generated because each type of kerogen is produced on the normal stage different hydrocarbon. In the type 1, generating potential maturity behavior, also in the type 1, we'll discuss it in detail. We have four type of the kerogen, type 1, type 2, type 3, type 4. Here, this is an example. This is Van Crevelen diagram. It's the relation between oxygen and hydrogen index. Type 1 here, it is mainly, it can give you oil. At the final stage, maybe give you some wet gases or dry gases. If you increase the maturity or you can increase the temperature. For the type 2, type 1, type 2, it is mainly produce oil. Type 3 is mainly can give you oil and gas, but the major is gas. Type 4 is to give you nothing because type 4 is reached to the final and maybe CO2 or andesite is called cool. What is the kerogen? Kerogen is formed from organic matter, algae, plants, microorganisms. We have different types of the kerogen, lignite, liptonite, kerogen. All of this one can be analyzed to give you whether oil or gas. Deposited in the sedimentary transformed during the diagenesis. We have three stages of from the Van Crevelen diagram analysis of your field. Diagenesis, it's a kerogen stage. Catagenesis, it is what we called it oil window. Metagenesis, which we call gas window, and metamorphism is the final stage, which we can call coal and CO2. Main kerogen type 1, 2, 3, 4, as we mentioned, the four type. Type 1, this type characterized by having a high initial hydrogen to carbon atomic ratio. This one, its primary source rock coming from the algal sediment. Algal sediments called allignite. Kerogen is the best source for oil-prone maturation. And this source maybe is very rare. I work in different areas. I didn't found the type kerogen 1, I think in areas that I work on it. Type 2, this type kerogen has relatively high hydrocarbon ratio, low oxygen ratio. It's called axenite. This is marine sediments. It's coming from the organic matter, bacterial, planktonic, and xanthonic. It's good oil or gas-prone kerogen. Maybe give you here, give you some oil and some gas associated with it. It is the main type for the gas present on the Mediterranean and Nile Delta. This is mainly type kerogen type 3, sorry, type 2. This is oil. Oil here, the main source is we found in Gulf of Mexico, Arabian Gulf, Saudi Arabia, and Gulf of Suez. The main type kerogen is type kerogen 2. Type kerogen 3 is the major, sorry, it's in the Mediterranean because it is mainly produced gas. It characterized by low hydrocarbon ratio, HC ratio, and high oxygen carbon ratio. The main storage of kerogen is the continental plants. This is why it is a major on the Nile Delta and the Mediterranean. It's called vitrinite kerogen. It's this for oil. Actually, the oil window here will be just this is small one. It will be very, very narrow oil window just associated with the major gas present here. Type 1, as we see here, this is only mainly oil. Type 2, oil mainly with some recreation of the wet gases. And here type 3 will produce mainly gas with a very, very small narrow window. It's called fluid. Maybe we can call it not oil. We can call it fluid because as type 3, always the gas is always associated with the condensate. Condensate is a fluid, it's not a gas. If we consider it the API higher than 48 to 50, 55, this is the API for the condensate, the more quality fluid. It's associated mainly coming from type 3. Maybe it's coming from type 2, by the way, but you need a very high temperature to it, to thermal cracking this kerosene to end up with crack this kerosene to form and very, very light component is cracked and forming very light material from this kerosene, ended up with some gases present on it. Type 4, it is anertinite. This type of kerosene is usually associated with cool organic matter. And this is high oxidized. There is no hydrocarbon here. Each one of them have a hydrogen index and the favorable product of this kerosene. As I mentioned, this is just a very quick summary. Type 1 algal bodies, very good for oil, planktonic. Type 2, good for oil, higher green plants. Type 3, it's good for gas. Oxidized woody debris, this is larger and right. Kerosene type 1, 2, 3. Here we found hydrogen index. This data is coming from the geochemical analysis. Should be in the type 1 higher than 600. Produce oil, 600 to 30, 300 is oil and gas. Here this is gas and oil. And finally, there is 50, none. There is no produce for kerosene type 4. Transformation kerosene into oil and gas. This is a chart just showing the workflow of this kerosene. This is thermal maturity of the organic matter. We have three phases: diagenesis, which is a mature stage. This is dry gas, biogenic methane. We just for the unconventional and for the what we can call it not thermogenic, it's biogenic gases. Catagenesis, this is the main oil window, oil and wet gas condensate. Metagenesis is the gas window, thermogenic gases. Here, this is the depth and temperature increase. As your time and the depth temperature increase, you will follow it from this window to this window, from this window to gas window. Just one point to say is on the gas, there is two origin of the gas. The first origin is biogenic gas. Biogenic gas is just coming from the algal activity, especially in the shale. It's not reached to the thermal maturity. It's produced only dry gas, only methane, more than 89 or 87% C1 and very, very minor amount of ethane, C2, and there is no C3, C4. This is a dry gas, we call it dry gas. It's biogenic origin. It's not need temperature and the pressure. It can be formed in any other window. There's no window for it. For the gas, thermogenic gases, it should respecting the catagenesis and the metagenesis. It present at the metagenesis stage or this gas may be thermogenic and it's yielding on the last or late stage of the catagenesis. It will be oil and associated gas with it, as we mentioned in kerosene type 2. Actually, as this case, we found gases with thermogenic. So there is a different story between the biogenic gas and thermogenic gas. Transformation of kerosene into oil. This is gas. Diagenesis, microorganism called metagenesis converted to some organic debris. Catagenesis is kerosene decomposed, just decomposed, cracking, thermal cracking, not due to the increasing the temperature and the pressure, forming oil. Metagenesis is the final transformation. It's give you a smaller gas. Molecule are produced wet gas. Wet gas is a contain greater than 1% ethane, propane, and actually we ended up with dry gas in the most mature stage, which is called metamorphism. What is the objective of the 3D Basin modeling? The main objective is to decreasing the risk, as we mentioned before. Actually, it is a very, very important risk reduction, exploration strategy, is identifying an optimal drilling location, migration based on your migration pathways, production optimization, increasing the reservoir fluid dynamic and connectivity, just to discuss this in detail. Environmental impact acids like the CO2 present. CO2, if you have like an example, you have CO2 on your reservoir associated with your gas. CO2 is need a very high expensive acids to produce it because as a normal acid you can produce with more than 2%. If you increase this interval, if you come from source like Jurassic or a very high temperature, very high pressure source rock, you can associate it, your gas associated with the CO2 present. Also, you can detect this one or you can handle it with a very good mineralogy interpretation without using the 3D Basin model. It is one of the most important benefits or objective of your 3D Basin modeling, how you can deal with the CO2 present here. Geological control, the various geological control affecting the petroleum system, including sedimentation rate, burial history, which coming from the 1D model, you can detect it, tectonic activity, structure evolution, the effect of the structure on your model, heat flow through time and your current time, lithological and petrophysical properties like porosity, fluid pressure regime, also it is gas or oil, and also here it's not mentioned the compaction or the compaction analysis of your model, which is actually affecting the maturity. What we need, what's the geological data needed to input on our 3D Basin modeling? Accurate input data is critical for Basin modeling. Should include seismic data. This is needed for the structure and stratigraphic interpretation. We need well logs just to know the lithology, porosity, permeability, and temperature data. Geological maps for regional context and paleogeography. It's very important to know your reservoir. Geochemical data is for the source rock evaluation, rock characterization like TOC, kinetics, RO, temperature, and so on. Petrophysical data, this is needed for the rock properties just to know your reservoir and the data needed for your model. It's okay. For this slide, this is geochemical calibration. It's not needed. It's called rock eval pyrolysis. Rock eval pyrolysis is one of the most important geochemical techniques. It provides information about existing hydrocarbon, remaining generation potential, corrosion type, and thermal maturity. As we found here, this is a relation between oxygen index and the hydrogen index and equivalent. This is type 1, type 2, type 3. You should, after your analysis, you can get your data. Your data here is present, some of your data in Keratin type 3. Here it's a mix between type 3 and type 2. Here this is a major type 1. If your data is present here, you should know from the geochemical data. Now you added this point to your chart, and after that you can detect your Keratin type. Affecting of corrosion type, of course, is knowing from the pyrolysis your data or your predicting hydrocarbon present in your reservoir. If you have corrosion type 2, so you can expect from your reservoir to produce oil. If you found corrosion type 3, so you expect it to be mainly more gas at your reservoir. Output obtained from the pyrolysis is very important techniques used and also have a lot of literature talking about it. This funds tested and audit. So I prefer this paper is very important. We have three peaks are normal observed. S1 peak, S2, S3. S1 here represent already existing bitumen. S2 represent hydrocarbon generation of the kerosene. S3 represent produced by oxygen pairing component at high temperature. By each one of them together, you can know the hydrogen index. Hydrogen is always S2 divided to TOC, multiplying by 100 milligram per TOC. Oxygen index S3 TOC 100 milligram per TOC. It's use it. You use this 2 point just to draw oxygen index to hydrogen index as this model to know your corrosion type. Also, S1, S2 over the TOC, you can know the anisotrope if your source rock is produced or not. And also you can predict, and we can discuss this in detail in our workshop, inshallah. Hydrogen index, you can know the productivity coming by using the 1D model. By using the 1D model, you can expect how can you produce from this well 2,000 barrel, 1,000 barrel, 500 barrel. It's by using the equation coming from the pyrolysis data. Gas chromatograph, this is very important just to know the amount of C here is present from the gases. Its technique separate individual petroleum component Increasing carbon number, increasing the oil specific gravity, decreasing the API. Also, it's coming from the pyrolysis to soluble extract oil, the crude oil. Chromatograph here is the application, estimating oil versus gas. Amount of gas and amount of oil. Its greater level is a gas chromatograph determine the detailed composition of the fluid, either rock oil and oil to oil correlation to know the source and to know your evaluation. Vitrinite reflectance is the most wide used indicator to the thermal maturity. The most important one that we use to calibrate our maturity is the vitrinite reflectance is used and therefore source rock maturity. Vitrinite scale has been calibrated by maturity. Its oil may be correlated with zone through the petroleum generation flow. If your RO less than 0.55, yes, we call it immature. RO between 0.55 to 0.8, it's oil and gas generation. If your RO between 0.8 to 1, now it's cracking of oil to gas. Now you start, if you have here, this is what we call excursion type 2, maybe give you some gases. At here, now it's increasing temperature, increasing the maturity. Oil start to be cracking to form gas condensate zone that we called it this we found in our reservoir. If your RO between 1 to 2.5, now it is a dry gas generation. All your source rock here at this level will produce only gas. There is no any fluid present, only dry gas. Just here, this is an example for fluid migration modeling. This is a real data estimated from the software. This is an example for also from the published data on migration modeling, and very important. Migration modeling simulation hydrocarbon movement from source to trap. You just search for it. Different approaches included. We should use Darcy migration, so you can do Darcy flow, invasion percolation, build methods. In the Petro mode, you will find this three method. In the Trinity, you will find only one method, Darcy migration. The three method is present on the Petro mode. It's not present on the Trinity, unfortunately. So you can use each one of them based on your knowledge and your data present on your field. The most famous one is the Darcy flow. We use it in all our fields that we work on it. If you have rifting and have salt effectiveness and so on, you should use a different model. On our workshop, we will discuss this in detail, but due to the time of the after this time of the webinar, we will not go deep for this point. Okay, this simulation help evaluating charge risk, identify potential and accumulation. This is an real example from Qatar. Traditional Basin modeling, it's constrained. Most of input parameter here. This is the prospect. It's a north field. This is Adi Shark. This is another prospect. All these green lines, green polygon, this represent the gas producer area at Qatar. Here, this is the major one. The north field is produce gas because it is coming with the red prospect is filled with gas. On the model, it is identical. Gas is red, oil is green, blue is unmatured. So this is an example show approach of the migration modeling. It's matching the existing fields. Actually here, the model coming filled all the after we use the data, all the data here. So this is a well. There's a lot of well drilled at this level. This is all as well. This is vertical. Actually, the migration of busways reached to this prospect for the oil. The oil here reached to the oil prospect that's already produced from well, and the gas prospect which already produced from many wells here. The migration reached to it is a gas migration. So at this level, your model is right. The migration fill and spill pass accumulation on the this is Arab deformation immediately above the source. This is coming from the vertical migration. The source is below the reservoir. The orange colored here accumulation are in the Cretaceous. Shuhaib formation is source from Hanifa T2 seem to be match or accumulation. Shaheen field in the Cretaceous spot. This is the one with the produced gas. Migration in the Arab are most horizon exhibit on the deeper flank. Uh, so less maturity have enough column to be built, cause leaking into the Cretaceous. Inside the model, all the model is valid. This map derived from the well data used hydrodynamic migration on the Cretaceous. This approach matches existing field and the minimum geological model allow calibration migration to the local geology of the field. Actually, we used all the data on our hand to build the model, and after that, we QC our model by the data drilled by a well. Shaheen here, this field is not produced, and we know it's not produced because it's the flank of the reservoirs. There is no trapping here. The migration pathways didn't reach to this one. So after we drill this well is the only one dry well here. So this is a practical example from Qatar how migration model can be calibrated against existing discoveries. We have discoveries, we have prospect. We now know why this well, some of this well is failure, some of this well is produced, and the produce from this well is matching our model. Using a simple geological framework, model successfully present no accumulation and to predict additional opportunities. This highlights one of the greater strengths of the Basin modeling prediction. Actually, here, this is a very good exercise. And this, by the way, this is a real data. It's already, by the way, published. You'll found in the website and on the trend software. They done this exercise. Another case study, this is from Gulf of Mexico, which we can call GOM, saprophytic hydrocarbon province. Excellent case study for the 3D based modeling due to the complex geology at this reservoir. In Qatar, this is a very simple geology. There is no major falls. There is no complexity of reservoir. And the Gulf of Mexico, it's a different story. Gulf of Mexico is a very complicated geology, including extensive salt tectonic and the deep water environment. The Gulf of Mexico here is characterized by six sediment succession, numerous salt debris, and complex history, rifting, and subsidence sedimentation. This feature create diversity petroleum system. From the model, the most challenge we face salt tectonics, complex geometrics, deep water environment, high pressure, high temperature, high pressure, low temperature, affecting fluid behavior. Of course, if you increase the pressure, if you increase the maturity, but lowering the pressure will also affect the maturity, and this is a major challenge on the Gulf of Mexico. Complex migration, there is a multiple source rock interact migration pathways, data integration. Here is combining amount of seismic and well geological data. You know the field is very high amount of data. You should connect all this data together to build a robust model. Application of the 3D based modeling on Gulf of Mexico exploration. It's extensive used. Predict source rock maturity, hydrocarbon generation, map migration pathways, asset trap integrity, evaluate prospect and unexplored area. Finally, the 3D based modeling is a major rule evaluating subsalt prospect, predicting maturity, understanding migration around salt bodies, which is a very critical issue, especially in the presence of the salt, reduction, exploration risk. Finally, that brings us to the end of our today's webinar. I hope this session has demonstrated how Bayesian modeling transforms geological data into predictive insight, enabling more information and exploration decision. Whether used in conventional petroleum system, frontier basin, geothermal project, or carbon storage studies, you need 3D Bayesian modeling. Bayesian modeling should be indisable technology. Thank you all. Thanks very much for your attention. Uh, I would know how be delighted to answer any of your question you have. You can open the discussion now. Let's turn to the chat. Anyone want to ask a question? What the software version of the lecture uses, please? Use better mode and the Trinity software. There is the two major software or three major software working on the 3D based modeling. Actually, we have Trinity software. Trinity software is a good software, but actually it's dealing with only one equation, one-way method, Darcy equation or Darcy flow. Actually, there is have a lot of issues in the lateral migration. Uh, on the more expertise, on the more fields I work in it, they didn't prefer Trinity. Trinity is a good software if you want to run a very, very fast model. Maybe if you're using Trinity with only 1 week, you can end up the 3D Basin modeling at home. It is just not a complicated step, it's just workflow, running the software. Step one, two, three, four, five, six, I end it. Another software, which is the power software, is a Petro mode. Petro mode is just more specific, more equation. He can use it very, very well in the complex basin. And also there is a connection now between Petrel, this is the third software, Petrel and Petro mode. The same workflow of the Petro mode, we can run it with the Petrel software. There is another module يعني SLP is just improved in the Petrel called the exploration geology. Exploration geology, you can hold the data from the Petro mode, entering the Petrel, and you can work with the 1D, 2D, 3D model. The main benefits of the Petro mode is not present in the Trinity, the more equation, more interpretation. For the Petrel, this is my opinion from my experience fields I work on it. I prefer Petrel because Petrel uh, you can use all the workflow from the Petro mode used on it, and also the main issue of the Petro mode, you can use the lithology as an interpretation as a facies, but you cannot distribute this facies for the Petro mode. This is an issue in the Petro mode. You cannot do it if you want to do it correctly, because also the facies and the distribution of your lithology is affecting the maturity, affecting the porosity, the compaction. The Petrel is more better at this point because the Petrel you can run 3D Basin modeling, 3D static model, and use it as the enter stage on the 2D and the 3D model. It will give you a more robust interpretation or a more robust 1D model and 3D model coming from the Petrel. For me, I didn't use Petro mode as a single because the reason of the fishes is not you cannot distribute it in the Petro mode. I use Petrel and Petro mode together. I prefer always to use this software together if you run the 3D Basin modeling, just to take it in your consideration lithology, matrix component, faces distribution. Also, it will decreasing the risk very, very, very good in the Petrel between the wells. So I didn't prefer to use only Petro mode as a single software to use in the 3D Basin modeling. I prefer to use Petro mode with Petrel. I prefer to use this one, and I just use the Petro mode alone and Petro mode and the Petrel. I get a more robust result using this two skill together. Also in the Petrel, you can make the 1D model and their calibration on the Petrel as well. I think on the next couple of years, I think Petro mode will be just a single module in the Petrel. It's better because Petrel take all the data from the Petro mode just from the exploration geology module in the Petrel, and you can do whatever you need using the Petrel software. Okay, let's stop sharing my screen and return back to the question. Okay. Mr. Ahmed asked how to get S1, S2, S3. S1, S2, S3, you can get it only from the geochemical data analysis. You should take a sample from your well, just give it to another company working on this analysis and making this pyrolysis test. Pyrolysis test is need a lot of tools just to get it to increasing the temperature gradually on your sample, geochemical sample exactly. Washing, preparing sample with different ways than prepare of the different sample. Then we make the pyrolysis test to get S1, S2, S3. From S1, S2, S3, you can get a lot of information. We can discuss it in detail on our workshop, inshallah. But there is no way to estimate S1, S2 from logs. It is just using geochemical data. Can I use can I use Betrel and well flow? Yes, you can use Betrel alone. By the way, because the Betrel simulation geology module, the Petro mode is present on it. You can remove your data from you can run the data model on the Petro mode and just convert it to the Betrel, or you can work on a Betrel at once. يعني this is in the Betrel, it's very easy. And by the way, some steps on the Petro mode need at least 8 hours just to like the maturity or the history match of the head flows during time. If you can thriftic or some structure, you need a lot of hours just to run this model. In the Betrel, it's just like that. يعني less than 10 minutes you can run this model. As there are any source to learn how to use better mode, you can use I think the only one released for the better mode workflow. I think it's present on the internet. Yes, there is just like PDF and the better mode. You can explain in detail the 1D, 2D, and 3D. On the Betrel, I don't think so because it's present. If you should have license file, license Betrel modules, and this is legal because some other case you will give you the access to know the workflow for your module. Confused about difference between thermal maturity stage and corrosion type. Type 1, 10%. So it is to be determined whether a source rock generates covalent gas. Arcasian type also. So the two concept generation. Yes. Corrosion type. This is good question from our colleague Mr. Fatin Zidane. There is a difference between maturity stage, diagenesis, catagenesis, and metagenesis, and corrosion type, type 1, type 2, type 3. Corrosion type, as all, corrosion type 1, on the normal case, it will produce oil. But if you have corrosion type 1, just give you an example. Of course, on detecting the oil or the window, you should depend on both together. Because in Petro mode, the first question he will ask you before we run the simulation, he ask you, what is the corrosion type of your source rock? He ask about the TOC and the corrosion type. So you should know your corrosion type because the corrosion type always give you the window of your expected hydrocarbon, oil, and gas. I didn't just prepare some slides. This question, I give you this example, but maybe I can prepare this couple of slides, explain each one of them, and I share it with Mega Plus. You can obtain it with from our colleagues in Mega Plus. Keratin type 1 mainly produce oil, but this is in a normal case. It will produce. But if you increase the temperature on it, the thermal cracking will occur to this keratin. After that, it's produced mainly oil. The oil is thermal cracking due to increasing the temperature and pressure on it. At this case, you will end up with this oil will become wet gas. And if you increase more and more, this is what you call in the catagenesis. Keratin type 1 catagenesis will produce mainly oil. After you increase the temperature and the pressure, you will just out from the catagenesis to metagenesis stage, increasing this one. The oil, the thermal cracking, it will be cracked and forming at this level mainly gas. So this type of gas is not coming from Keratin type 3, which is normal, but it's due to the thermal cracking of the Keratin type 1. It's by increasing the pressure and temperature on it. So you cannot use only Keratin type, you cannot use only the catagenesis and the metagenesis alone. You should use all this data integrated together in your model. By the way, the model in the better model and the Betrel will ask you for all this question because it is mandatory to know the maturity. Uh, this is two different concepts. You should not use one of them alone. You should not just consider only one. You should use all those together. I hope it will be fine. I had this idea to use CMC, Petrel, and as for modeling and use their data. Okay, this is good. You should use all of this. Thanks for you. So such nice presentation. No, thanks for you. Many thanks for you all. Are you recommended TensorFlow basic and lab for 3D Basin modeling? Uh, Actually, uh, I didn't prefer one equation for all. I prefer to know your data. Uh, each model or each field have a different story. You should know your model, you should know your fields, you should know your corrosion type, you should know the if the field is already produced, know the type and the analysis of your hydrocarbon. It is mandatory before we choose the equation or choose the workflow needed for the 3D Basin modeling. There is no stable workflow. There is no only one that is unique for all the fields. No, email, please. Okay, I can share presentation. No problem. Thanks for you. Okay. Yes. So much. Very good explanation. Thanks for you all. Yes, I think Mega Blast on the channel of the YouTube is coming the webinar, including all the presentation, including all the record, all the answers the question. It will be available. يعني our coordinator answers this question. Okay, is there any other question? Did anyone want to ask about anything?
Yes, hello?
Yes, please.
Yes, okay, first thing, let me say thank you. Apparently, I missed the schedule of the presentation, so I didn't see any part of the presentation, only the question, so, but I will still ask my question. So I like to know, you said when we build the model, the model will leave all of this information carried in type and so. Does the model allow you to have two carriage type? Is there provision for two carriage type or just because like in my country we built two
Yeah.
exploratory well and then we have a source rock that is both type one and type two. So
Yes.
if I want to build a basin model for my area or for the basin where I'm working,
Yeah.
will I do them separately or is there space in the model where I can put type one and type two? That's my question.
Yes, I didn't catch the last question, but I think you asked about if you have in your basin type one and the type two source rock. If you wanted to just make a 3D basin modeling, how you can handle these two together, right?
Exactly. Yes. If
Yeah.
you're doing a 1D, if you're doing a 1D basic modeling, how can you handle the two type as being recorded from source raw
Actually, actually, actually,
analysis?
actually, actually, Mr. Harris, I work in a field. They have the four different type. Exhibit type one. It's very easy. You should model everyone alone and just make their maturity and the temperature for it and so on. You will make the workflow for both of them because if you have two different types of corrosion present on your fields, so that you mean you have different fluid or the fluid that's not coming from the same source. Finally, you should know you should model the type 1 and type 2, each one alone. You should model each one of them. And by the way, if you have different source rock with the same corrosion type, I work on this on the Mediterranean. We have uh, corrosion type 3, but we have different four source rock. At this case, you will model each one alone. And after that, if your field is produced, you should take a chromatograph analysis or oil analysis just to see which one of them feeding your reservoir. So if you have two different kerogen or you have a two or three or four different type of the source rock, you should model each one alone. And after that, compare it to the real data which coming from your well. Just to know if you have a production data, it is more better and better. In this case, I know the oil quality, I know the oil type, I know the gas analysis, I know the gas chromatograph. At this case, I return it back to see the fingerprint for each one of them to which type of the kerosene present. I give you just an example. If I have type 1, I know this is oil, mainly oil. If I have two reservoirs with oil and gas, of course type 1 will feeding the oil. This is confirmed. But if you have just example oil and gas in the reservoir and I have kerosene type 2 and kerosene type 3, no. As this case, it is very critical. I will work in each kerosene type on the source because of course two different kerosene type, of course two different source. Because the source it will not feeding type 2 and type 3 at the same time. It's of course two different source. At this case, I modeled source number 1 and see the fingerprint for it for the analysis of the printan fintan ratio just to see the environment and compare it to the type of the hydrocarbon present on our reservoir. If it's matched, so it's from this level. It's not matched at this case, I will return it to source type 3 and model it, and after that I will compare this to what was produced.
Okay,
So
so
if you have, okay,
a follow-up question to that. Okay, let's assume that we have type 2, which is a mix of gas and some oil because of the
yeah.
transition of the organic matter and stuff. So, how do we are considering that it's a type 2. So, what is it that, because you, for instance, you say that if we, our type 2, you, solution gas, solution, solution gas reservoir, or is it a different kerosene type that contribute to solution gas reservoir? Because we know that there are some reservoir that occur purely with gas in solution, and some occur as isolated gas or as gas cap also. So how will you explain the phenomenon relative to the source rock and the distribution in the different reservoir solution gas and maybe associated gas? Thank you.
This is very good question. Uh, if your oil, if your oil, now I catch your question. If your oil have the same maturity, Mr. is asking if I have kerosene type 2, maybe I have a solution gas and I have oil as well. So maybe I have oil and gas. And kerosene type 3, it's mainly produce gas. If I have this level, so if it's gas, I will produce gas with some light hydrocarbon, which called condensate. So I know it's very easy. But if you have a gas and oil in my reservoir, I cannot differentiate using which one of them is feeding my reservoir. It's very easy. Let's see at this level, you can take a sample from your oil and the fume gas. If both of them, gas and oil, have the same maturity, so you expected this coming from the same source. As this case, you mentioned exactly it's Kirschner type 2. I expect this gas will be a solution. Is coming. Is mainly Kirschner type 2 is mainly gas. Is mainly oil. Sorry, with some associated gas. At this level, if you entering your reservoir, but the fluid coming from this Kirschner type 2, you will find gas and oil. At this case, you will get the same maturity. The gas will be maturity around 0.85 as example, and the oil will be the same 0.85. So if they are sharing the same maturity, at this level, it's coming from the same source. But at some cases, you found oil 0.85 RO maturity. This is the oil, and the gas is 1.2 or 1.3. At this case, you should know there is two phase of the migration. First one, it is the less maturity, which is the oil at this case, is coming maybe from Keratin type 2. And after that, the oil, the gas is coming with a more mature stage coming from the different source rock. By the way, maybe you will get the fingerprint or the isotope analysis. It is very mandatory because at some cases, at some rare cases, maybe you have the oil less maturity 0.8 and the gas is 1.2 and they coming from the same source. But at this case, you don't have one single migration phase. You have two migration phase. Okay. First one coming from the oil window, which is mainly produce oil and oil entering your reservoir. And after that, increasing the depth of your this source rock and increasing the compaction, thermal cracking occur to your oil, increasing the maturity to 1.2, start gas to be liberated and coming from this source rock, and after that is trapping on your reservoir. So maybe at this level, this two type of hydrocarbon, gas and oil coming from the same source rock, but with different maturity. How can I know this point? The only one is using the one from the TD model 2D or 3D. Just backstripping for the taking just 2D line passing from your kitchen that you have a doubt confirmation that the main source rock in your area reaching to your well or your produced polygon reservoir. And after you draw this line from the 3D or the 2D model, now backstripping the steps for this source rock from the 20 million year example until 0 million years and see the capability of your source rock to produce both hydrocarbon, gas, and oil at the same time. We can solve this issue with the 3D Basin modeling, but with the 1D, no, there's no solution. At scale, Basin scale, epistemology, server.
Thank you so much. Maybe when we go in
No,
depth to do the course, maybe we have more better understanding. But that's good. Thank you for the response. Thank you.
no, thanks for you. Anytime. Thermal geometrization and that scale, Basin scale. To thermal geometrization, can we have an idea about oil maturation? Yes. At the Basin modeling, this is a good question. We can get oil maturation. This is exactly what I explained to Mr. Ya's question. Oil maturation is very important to know from this model, also from 1D, 2D, 3D. Oil maturation is affected by the temperature and RO. If you have this data and the good calibration, you can know your oil maturation and oil window as well. Each one of them have different maturation. Maybe you found oil at 0.8 and maybe you found oil at 1.2. This is the early oil window, and 1.2 it is the late oil window. Of course, it will be different, and of course the API will be different, and also the oil quality will be totally different. Okay. Any other question? Thanks for you all. Thanks for your attention. Thanks for your question. Thanks for your communication. If anyone have any question, I will be available. Just ask me, and I will answer any of your question. Thank you all.
Yeah,
Thanks
thank you
for you.
too.
Thanks
Yeah,
for
thank you.
our collision Mega Plus. Thanks for you.
No, thank you, Dr. Mahmoud. Thank you, everyone, for your time and attention. We truly appreciate for joining today. Again, a very special thank you to Dr. Mahmoud for delivering such a valuable presentation and for sharing all your knowledge. We really appreciate. You will be able to find this webinar in our Mega Plus YouTube channel, and also we will contact you to share the certification that we set. And okay, if we don't have more questions, thank you to all of you again, and have a wonderful rest of the day. Thank you. Goodbye.
Bye bye.
Bye bye.